A very good day to all of you. I'm Dr. R. Sridhar from Electrical and Electronics Engineering Department, SRM Institute of Science and Technology, Kottanukulattur. In this session, we will see how to simulate a half-wave controlled rectifier in a MATLAB environment. Before getting into any simulation environment, we should be aware of the concepts behind that circuitry. So before getting into the MATLAB simulation, let us see how a half-wave rectifier functions. So half-wave rectifier essentially consists of a thyristor, one thyristor whose anode and cathode can be denoted as shown here, and this terminal is gate terminal, which is the controlling terminal. So your input voltage is Vs, nothing but Vm sine omega t, and you have a resistive load. We can see for RL load also. First, let us see for R load. Okay. The concept behind the circuitry is when positive half cycle is there, this SCR is forward bias and it is ready for conduction. And you know that SCR's condition for conduction is the condition for conduction is condition for SCR conduction is one, the VAK should be fed a positive, a forward bias. Next, your anode to cathode current IA should be greater than that of your latching current. So once you trigger this, both of the conditions are complied with, then only there will be conduction. So at this instant, say omega t is equal to 0, the SCR is ready for conduction, but it waits for the triggering angle, which is here given with the firing angle of the delay of say alpha degree. Let us take alpha is equal to 45 degree. Okay, so you are turning on this thyristor after 45 degree. Fine. So once the triggering pulse at 45 degree is given, the SCR acts like a short circuit conductor. So the switch is on at alpha is equal to 45 degree. So your input voltage will get replicated in the output. Fine. And with regard to this particular waveform I naught, hope you will not have any issue with that because it is an R load. So the R load, in R load, the current and the voltage will be in phase and the profile remains the same. Probably the magnitude of this I naught depends upon your R value. So the peak is Vm by R. So the takeaway points from here is the SCR is ready for conduction at alpha is equal to 0, but only when alpha is equal to 45 degree, we latch this on. So then only the SCR conducts. And again at this point, SCR goes to off state automatically because its current, anode to cathode current, goes lesser than its latching current because of this reverse bias, right? So this condition again is complied at this junction. So SCR gets off. So once SCR gets off, there will be no current flow and there will be no voltage across your thyristor. So mathematically, when you try to write an expression for this, all you need to do is V naught is equal to the total time period 1 by 2 pi, then integration of alpha to pi 1 by 2 pi alpha to pi. I'll write this legibly. So this is alpha. The input voltage Vs, nothing but Vm sine omega t d omega t. So when you try to integrate this, you will get Vm by 2 pi 1 plus cos alpha. So this is the average voltage of a half wave rectifier. So all you need to understand this is you have a control over your firing angle. So when you change your firing angle, automatically your average output voltage is also changed, right? So this is the performance of uh, a rectifier. So the commutation here happens naturally. So it is called as natural commutation, or phase commutation, phase commutation, or sometimes it can be termed as line commutation. That's fine. So with this background, let us try to get into the simulation environment and check how it gets simulated. So already I have constructed the MATLAB diagram. For the beginners, let me quickly say from where I have taken all these components. So from this circuitry, I inferred that I need a source, I need a thyristor, I need a load value. Of course, we can have first R load. Okay, I need a load, and then of course I need a scope to see my waveforms, and the brain behind the circuit is the pulse generator. This component I need, and I need to measure my current and voltage, so I need to take these measuring devices also. So let us check from where I should take all these components. So in MATLAB, you please remember that you need to, as far as Simulink is concerned, you majorly have these business with only these things: sync, sources, Simscape, right? Under Simscape, you have specialized technology, right? So under this only, you have all your blocks, simulation blocks, electrical simulation blocks is there. Okay, so these are the things that you need. Peripherally you need this is vital thing, and different version will have different name of this block set. What I am trying to simulate is 2014 a version, where under Simscape you have a specialized technology. In earlier version, I remember that you may have a block called power systems sim power systems, under which you can find all your electrical blocks. Okay, let us see in MATLAB how it can be done. So let me quickly say you from where I took all these components. So let me directly go to Simscape, and in specialized technology, I find first is I need a source. So I will take a AC voltage source. I can take it. That's fine. Then I need a thyristor. So I find a block called power electronics. Definitely under this, I can drag and put it. Then I need a resistance. You need to be careful. You should not take RLC load, rather you should take RLC branch. And if you are having business only with R load, change into R load. That's fine. And then what I need, then of course I need measuring instruments. So in measurements, I can see that I need current and voltage measurements. So I can take those couple of measuring devices, my current and voltage measurements. Then of course I need my pulse generator, which is there in this peripheral sources. So I'll take the peculiar component pulse generator. Okay, where is my pulse generator? Yes, it's here. I'll take my pulse generator, and then if I want to measure the value in terms of value, you need to take display. If you want to you are only interested in seeing the graph, you take scope. So these are the components that you need to take from these three block sets predominantly. One is Simscape, specialized technology, sync, and sources. So let me delete all these things. So by using this, I have constructed, and the scope, when I double click it, you can find an axis. All I have done is I have done for 4 axes, a 2 1. You can also have each waveform you can see in a separate scope. Also, for better understanding, I have taken scope and I have given in different panes in a single scope. That's fine. So right, so now I need to give the values. So when you see here peak amplitude, what I have done is 220 into, because it's amplitude, I'm trying to give RMS into root 2. That's why amplitude is off. And frequency, prior to my adjustment, probably it would have been 60. To change that into 50 hertz. After all, we follow 50. Then load, okay, 10 ohm or 20 ohm, it's up to you. You can have it. And here, this is the trickier part of the whole simulation you need to be aware of. Amplitude, it's fine. Amplitude in practical cases, for a VGK, you may have 12 volt to 15 volt. So I have given 15 volt. And in simulation environment, it's not a big deal. You can give lesser voltages also. And in period, you need to give 0.02 second. Hope you understood why I have given 0.02 second. It is nothing but the frequency I have taken is 50 hertz. So 1 by 50 is 20 millisecond, 0.02. Pulse width, again, when you read SCR working, probably you will understand that the width of the pulse is not having much impact with the conduction of SCR. Once you give a pulse, SCR will be turning to on state, and the width of the pulse is not a big deal with the performance in SCR switching. Okay. Of course, you need to give the width of the pulse more than that of the on time, but here the width as 5%, 10%, anything is fine. And next comes the very critical part of this, where you need to give the firing angle. In the theoretical analysis, we saw that firing angle should be 45 degree. We took for 45 degree. Here, you see here, specifically, they have not given in terms of angle. Rather, they are particular about feeding it in terms of seconds. So all you need to do is you need to give this firing angle as 45 in terms of time. So you understood that the for a time period of 20 millisecond or 0.02, the whole cycle is 360 degree. So 0.02, and for a 45 degree, right, what is the time period? So all you need to do is 0.02 into 45 divided by 360. So that only I have given here, right? That only I have given as 45 into 0.02 by 360. So 45, it's up to you. It's right. The 45 degree is changeable. You can always change your firing angle. Here in this case, we have taken as a 45 degree. You can give 30 degree, 90 degree, whatever, depending upon your requirement. So now the simulation is ready. In some versions, you need this solver power guy. So once you try to try to run it, see to that this power guy block is there. How to take it? Take it here and simply type a power guy. You can find it and drag it and paste here. Now when you run it, so here the time period is 10. Most of the people will have 10, and then you will try to zoom it. So for better understanding, I have given 0.08. Why 0.08? I am trying to give for 4 cycles. So one cycle is 0.02, so 4 cycles. Right, now you see here how nicely the graphs comes. So I'm triggering at 45 degree. My voltage is, right, the output voltage is building at 45 degree slowly, and then it quenches off at 180 degree, right? Since it is a resistive load, whatever my profile of my voltage, that is the replication here in my current. So this is the half-wave rectifier. If it is an RL load, if it is an RL load instead of my R load, so imagine you have a RL load, not R load. So you have resistance and inductor. Imagine that this is an inductor. The problem here is the inductor will not make sure that this SCR turns on at pi. In earlier case, where SCR, right, the commutation happened is naturally at alpha degree equal to pi. But in the case of the inductive load, because of this inductor, your output voltage will not quench at alpha is equal to pi, rather it will go down and then come back, and then it settles again alpha equal to, okay, let me draw with an alpha, then you will understand. Yeah, alpha is equal to 45 degree, for example, right? 45 degree. So again for a 45 degree, I'll get fine. So why this curve comes? This curve, this dip in the negative part comes because of this inductance. So after zero crossing, this inductor stored current is discharged in this closed path. Because of that, the SCR does not turn off at this moment, rather it remains in on state. Once it remains in on state, you will get the negative part also of your source voltage. So if you draw the current, I need to draw likewise, because the current is right. So this part is because of inductor, frankly saying. Again here no current, and then again this current will go like this. Fine. So this is what the current waveform is of. Okay, in the case of an inductive load. So when inductance is there, definitely you will get a negative portion, right? Which is not recommended for good power quality or good power factor, because you have a negative part, current is in positive. So your net output power delivery will deteriorate, definitely, right? So we may have a freewheeling diode, that is a different part to discuss, right? As of now, you remember that when you put an inductive load, the voltage will have a negative portion also. Let us check in a simulation whether how the negative voltage comes. So all I will do is I will change that into RL load. Okay, and then let me check how it works. Fine. Now you see here, whatever I have shown in theoretically, you have got it. So the current you see here, the current also does not quench here, rather it quenches only at this point. So this is how the inductive. So you can do one thing, you can increase your inductance and check. So once you increase your inductance, I'm sure that this negative voltage will have further dip, right? So this is what I have for you as first experiment. Hope you understood the theoretical background of half-wave controlled rectifier, as well the simulation. So thank you, my dear students. We'll see in at another class. Thank you.